Okay, so the first step is to be able to make some observations about the running time of the programs. And for analysis of algorithms, that's easier than in a lot of scientific disciplines, as we'll see. For an running example, we're going to use the so-called three-sum problem. And it's an easy-to-state problem. If you've got n distinct integers, how many triples sum to exactly 0? For example, in this file 8ints.txt, which has 8 integers in it, there's 4 triples that sum to 0. 30 minus 40, 10, 30 minus 20 minus 10, and so forth. And so our goal is to write a program that can compute this quantity for any input file, any set of n integers. This is actually an extremely important computation that's deeply related to many problems in computational geometry, which is a branch of computer science that covers the algorithms and underlying science related to graphics and movies and geometric models of all sorts. So this is actually an important practical problem. But it's a simple one to write code for. Any of you could write down this program without much effort. It's got a static method count that is going to go ahead and take an integer array as argument. N is that's the number of integers, that's the length of the array. We'll start with a variable count equals 0. And then a triple for loop that checks each triple I, j, k. We go I from 1 to n, j from I plus 1 to n, and k from j plus 1 to n, so that we get each triple just once. And then if I plus j, ai plus aj plus ak equals 0, we increment the count. And after that triple for loop, we return the count. And then the main method in this simple class just reads in all the integers and prints out the count. So that's a brute force algorithm that is a fine method for solving the three-sum problem. Now what we're interested in is how much time does this take as a function of n? Well, one way to time a program is to just look at the watch. If you have a stopwatch, or look at the clock, or your phone, whatever you might need, you can just go ahead and time it if you want. We have, Java has as part of its standard library a stopwatch class that will go ahead and compute elapsed time. Anytime you run a program, if it's set up to easily take input of different sizes, a natural thing to do is just run it for bigger sizes. So for 8 ints, this program takes not too much time. For 1,000 ints, it takes half a second. For 2,000, it takes more time. That's 3.7 seconds. Run it again, still takes 3.7 seconds. For 4,000, so each time we're doubling the size of the input, and it's definitely taking more time each time. And actually, as we'll see, if programmers who get in the habit of testing the running time of their program in this way can get so that you can actually pretty easily and quickly evaluate when it's going to finish. In fact, while you're waiting for it to finish, you can often figure it out. So that one took 30 seconds for 4K, and definitely we could figure out how long it's going to take for 8K before it finishes. And you'll see how in just a second. I'm not going to wait right now. You can think about what you think. Okay, so that's empirical analysis. Run it for various input sizes and measure the running time. Now, if this were some scientific problem where we were counting something that happened in the natural world, the number of ants on an anthill or whatever, then we'd have only a few data points, and we would try to understand what's going on by doing a plot of our running time, the quantity we're interested in on the y-axis, and the problem size on the x-axis. We get a curve like this. And actually, what scientists usually do, because so many problems fall into this class, is do the plot as a log-log plot. If you do it as a log-log plot, very often you'll get a straight line. And the slope of the straight line is the key to what's going on. In this case, the slope of the straight line is 3. And so you can run what's called a regression to fit the straight line through the data points. And then it's not difficult to show, to do the math to show that if you get a straight line and the slope is b, then your function is proportional to a n to the b. That's called a power law. And that's true of many, many scientific problems, including most algorithms. So here's a little bit of the math for that. So the straight line means that since we did a log-log plot with powers of 2, that log base 2 of t of n equals b log of n plus c. And we have our empirical values of b and c. And then if you raise both sides of that equation to 2 to that power, then you get t of n equals a constant times n to the b. So right away, just from observation, we have a pretty good model for the running time of our program. We can do the math and figure out that it seems as though the running time is about 10 to the minus 10 times n cubed seconds. And we can use that hypothesis to go ahead and make predictions. Just plug in for different values of n, and it says it ought to take us 400 seconds for 16,000. And 400 seconds is plenty of time, but now we can go ahead and invest and run that experiment, and sure enough, we're pretty close to that 408 seconds when we run it. And now we can make a prediction for 32,000 or for whatever else we might be interested in. The model helps us do predictions without investing the expense to run the experiments. In fact, in this situation, if there is a power law, and again, in very great majority of computer algorithm running times, it's going to be a power law. What we can do is just double the size of the input each time, the way we were, and then take the ratio of the running times for n and 2n. And if you do that, that ratio is going to converge to a constant. And in fact, the log of the ratio is going to converge to that constant, which is the exponent of n in the running time. And just need a little math to check that one, but that's a very easy and natural way to go ahead and predict running times. So that's what I said before is, so we have this quick way to estimate B in the power law relationship. How do we estimate A? Well, we can just run it and solve for A. So once we've decided that that exponent is 3, let's run it for some big N, and we get a pretty close model to the one we had from plotting things. So it's almost identical hypothesis, and we just got it by running the program doubling n each time. Okay, so there's a lot of effects in trying to understand the running time of a program on your machine. So key effects are independent of what computer it is, and that's the algorithm you're using and what's the data. And that's going to really determine the exponent in the power law. And then there's a lot of system-dependent effects. What kind of hardware do you have? Do you have a fast computer or a slow one? What kind of software? What's going on in your computer? All of those things really determine the constant A in the power law. So in modern systems, there's so much going on in the hardware and software it's sometimes difficult to get really precise measurements. But on the other hand, we don't have to sacrifice animals or fly to another planet the way they do in other sciences. We can just run a huge number of experiments and usually take care of understanding these kinds of effects.